Welcome to Luvitex Engineering, where we sketch out the things that keep the industrial world moving. Now, let's start.
We're going to transform a highly technical engineering white paper into a complete masterclass on designing safer, more efficient fluid systems. Now, if you work with industrial fluid or analytical systems, you already know that achieving incredibly precise temperature, flow, and pressure settings is absolutely non-negotiable. So today, we're diving right into the art and science of pressure regulation. Let's kick things off with a pretty high-stakes question, one that literally every facility operator has to face at some point. What actually happens when the wrong pressure regulator gets installed in your system? You know, it's really easy to look at a regulator as just another piece of basic hardware, but the reality? This one specific choice completely dictates the operational integrity of your entire process. Because selecting the wrong component doesn't just mean you're going to have a bad day at the plant. An unwanted pressure drop leads to catastrophic system inefficiencies. And honestly, it gets worse, because an unwanted pressure increase can completely destroy highly sensitive, wildly expensive analytical equipment. In the absolute worst case scenario, you are looking at severe, life-threatening safety hazards for your personnel. The stakes truly couldn't be higher here. So, to make sure your systems operate flawlessly, we're going to break down this complex engineering framework into 5 clear, actionable steps. We'll cover the stakes, system conditions, regulator behavior, the loading element, and finally, operational best practices. All right, let's jump into Section 1, the stakes of pressure regulation and understanding your baseline, because getting a firm grip on your system's starting point is the absolute best way to prevent downstream disasters. By actively following these 5 steps, you essentially take all the guesswork out of your regulator selection. We're replacing trial and error with rigorous, bulletproof engineering. Moving right along to Section 2, system conditions and needs, focusing on fluid, pressure, and temperature. We really have to look at the unique physical conditions your regulator is going to face out in the trenches, and that starts with the physical behavior of your system media. Obviously, you need to know your expected maximum, minimum, and normal operating pressures, but you also absolutely must understand how temperature interacts with those pressures. Enter the Joule-Thomson effect. If you've ever held an aerosol can and felt it get freezing cold in your hand while you're spraying it, you've experienced this firsthand. The entire purpose of a regulator is to alter pressure, right? But with certain media, altering that pressure dramatically alters the temperature. Take compressed natural gas, for example. It can plummet from 20 degrees Celsius all the way down to a freezing negative 65 degrees Celsius purely because of a pressure drop. If you haven't accommodated for this, maybe with supplemental heating elements, your regulator is just going to freeze solid and completely stop functioning. Now, once you really understand your media, you're going to hit a critical crossroads regarding your control needs. Are you looking for a pressure-reducing regulator or a back pressure regulator? It basically boils down to this. If you need to step down the pressure from a high-pressure source before it hits your main process, you go with a pressure-reducing regulator. It controls your downstream pressure. But if you need to maintain your upstream pressure by venting excess fluid when conditions peak, then you need a back pressure regulator. They do completely opposite but equally vital jobs. Okay, Section 3. Decoding complex regulator behavior using the flow curve. Once we know what we need, we have to understand how these blind mechanical devices are actually going to behave in the real world. Keep in mind, regulators don't have electronic inputs telling them what to do. They are entirely mechanical and respond naturally to field conditions. The hard truth we all have to accept is that no regulator produces a perfectly flat horizontal flow curve. Sure, we all want to operate right in that nice, flat middle section, the ideal operating range where pressure stays consistent even when flow changes. But to survive, we really have to deconstruct the extremes on either side. So, way over on the far left of the flow curve, we have lockup, which is also known as seat load drop. This is that steep drop in pressure required to completely shut off the regulator. If your system forces the regulator to constantly operate in this near-zero flow state, the regulator is going to seriously struggle to maintain pressure. It might emit this terrifying chattering or pulsating sound before just abruptly snapping shut. You absolutely want to avoid operating your system in this zone. Then, swinging over to the far right, we hit choked flow. The really crucial takeaway here is that selecting a regulator solely based on its maximum flow capacity, or its CV, is just a total recipe for unsatisfactory performance. Why? Well, because at maximum flow, the poppet is thrown wide open. It completely loses its ability to actively control pressure and essentially just turns into a restricting hole in your pipe.
Now, keep in mind that different gases change the math completely.
Manufacturers usually generate their gas flow curves using nitrogen and their liquid curves using water or hydraulic oil. So if you're running high-density gases like hydrogen or helium, it's going to severely alter your sizing. It'll force the regulator to open much wider just to maintain equivalent flow rates, which in turn causes a much steeper drop in pressure. Next up, we have to account for SP, or the supply pressure effect. Sometimes called inlet dependency, this is a highly counterintuitive mechanical behavior. You really have to think of it like a seesaw. If your supply pressure upstream goes down, say a supply cylinder is emptying out, your outlet pressure downstream is actually going to be pushed up. Let's break down the math on that. A regulator's SPE is typically given as a ratio or a percentage. If your regulator has a 1% SPE, or a 1:100 ratio, that means for every 100 psi drop in your inlet pressure, your outlet pressure is going to dangerously increase by 1 psi. This is a massive factor during system startup or shutdown, and it can easily overpressurize your downstream equipment if you aren't ready for it. Wrapping up regulator behavior, we have hysteresis. Because of the dynamic friction forces happening inside the mechanical components of the regulator, your flow curve actually looks slightly different depending on whether flow is increasing or decreasing. If you return to a set flow rate after a temporary spike, the pressure might end up slightly higher than where it originally started. Because of this, it's always an operational best practice to approach your targeted set pressure from a lower pressure to make sure you get it exactly right. All right, section 4. Choosing the loading element and balancing those internal forces. Let's look at the internal components that actually make all of this happen. It usually boils down to contrasting these two primary choices. The spring-loaded regulator is your familiar, reliable workhorse. You turn an external knob and a spring pushes down on the sensing element. It is absolutely perfect for general-purpose applications. But on the other hand, we have the incredibly dynamic dome-loaded regulator. Instead of a physical spring, it uses pressurized gas housed in a dome chamber to flex the diaphragm. This kind of fluid control gives you a much flatter flow curve, lower droop, and just incredibly high precision for your highly sensitive applications. Which brings us to our final stop, Section 5, operational best practices to actually prevent failure. Because look, even the most perfect hardware is eventually going to succumb to wear and tear. Let's talk about the absolute most common and arguably the most threatening maintenance issue out there, a phenomenon known as creep. Now, creep is not some natural behavior of a flow curve. It is a highly dangerous mechanical failure. It happens when a tiny, microscopic foreign contaminant gets stuck, creating just a hairline gap between the seat and the poppet. System media sneaks right through that gap even when the regulator is technically closed, building up this unwanted, creeping pressure that can totally obliterate downstream components that simply aren't rated to handle it.
So how do we cure this? You have to strictly implement 3 things. First up, install clean filters directly upstream of the regulator to catch that debris. Second, use properly rated relief valves downstream to safely vent off any of that creeping pressure before it causes any actual damage. And third, always keep spare parts kits readily on hand. That way you can fix the seat and pop it immediately, completely avoiding massive system downtime while you wait around for shipping.
The source material from Swaglock really hits the nail on the head here. It reminds us that your regulator is, at the end of the day, a blind mechanical device. There are no electronic sensors, no self-diagnostics. Its longevity and honestly the safety of your entire team relies entirely on your diligent oversight and proactive maintenance. So we've laid out the 5-step framework to diagnose, select, and maintain the regulators in your fluid systems. You know exactly how to read those flow curves, how to accommodate the Joule-Thomson effect, and how to aggressively combat creep. I want you to look critically at your own facility today. Are your regulators an invisible shield actively protecting your process, or are they a ticking time bomb, silently setting the stage for a massive failure?
Thanks for watching. For more industrial insights, check out our other videos. Don't forget to like, share, and subscribe to Luvitex Engineering.